Hello friends, today I am going to discuss univariate time series models. Just I have discussed something like time series and model with more detail, but whenever I am going to talk about like a univariate, so need to understand some basics like ER models. So AR model is called a auto-regressive model. So the AR model is the most basic building block of univariate time series. So univariate time series are a family of models that use only informations about the past of the target variable to forecast its future. They do not rely on other explanatory variables. So similarly, univariate time series models can be understand as a building block, means they add up from the simplest model to a complex model, and that combined the different effects described by an individual model. So AR model is the simplest model of the univariate time series model. So AR means auto regressive model, we'll say, and just after some time we will learn moving average MA, ARIMA, combinations of AR and MA model, ARIMA adding a differentiations to the ARIMA model, S ARIMA, S ARIMAX. So here auto correlations, first we have to understand AR means auto regressive model. So before that you have to understand, because I have already discussed auto correlation. So the auto correlations, the past influence the present. So auto-regressive model describe the relationship between the present of the variable and its past. So it is therefore suitable for variables in which the past and present value correlated. So as an suppose like I am waiting line at the doctor, like for appointment, and imagine that the doctor has a plan in which each patient has a 20 minutes with them. If every patient takes the exactly 20 minutes, this works fine. But what if the patient takes a bit more time? An autocorrelation could be present if the duration of the consultations has an impact on the durations of next consultations. So if the doctor needs to speed up the consultations because the previous consultations took too long, so you observe the correlations between the past and present. Past value influence the future value. So this is the concept for auto correlation. Similarly, we can take another example of compute the auto correlation in earthquake counts. So we will see something like earthquake data sets. The data sets is collected by the some US National Earthquake Information Center. Otherwise, you can also collect from Kaggle's. So, and we can easily describe this data. So, now other things, if you like to understand something like a pattern, so you have to write the sum code, and then you can easily understand uh, this type of autocorrelations. So now you can try to understand positive or negative autocorrelations. So the correlations just we have already discussed. Irregular correlations, autocorrelations can be a positive or negative. Positive autocorrelations means that a high value now will likely give a high value in the next period, and this can for some like if I am going to be observed in a stock trading, as soon as many people want to buy a stocks, so its price goes up. This positive trend makes a people want to buy this stock even more, as it has a positive result. The more people buy the stock and more it goes up, and more people may want to buy it. So positive correlations also work on downtrend. So if today stock value is low, then it is likely that the tomorrow value would be even lower. So as a people start selling, so when a lot of people sell, the value drop, and even more people will want to sell. This is also a case of positive autocorrelation, as the past and the present go in the same direction. So if the past is low, the present is low, and if the past is high, present is high. So these are called a positive autocorrelations. Negative autocorrelations exist if the two trends are opposite, and this is the case in the doctor's consultation durations example. So if one consultation takes longer, the next one will take shorter. If one consultation takes less time, the doctor may take bit more time on the next one. So you have to understand, you have to observe the correlations of the around, like suppose if we write here the 0.31 between the current year and past year, so this correlation is a positive rather than negative, as was the expected based on the graph. So this correlation is of a medium strength. It seems that the correlation has captured the trend in the data. So if you look at the graph, you can see that there is a trend in the number of the earthquake, a bit higher in the earlier year and then a bit lower for the certain period, and the last year bit higher. Again, this is the problem, as a trend is not a relationship if you want to capture it. Another thing we have to understand, like mm, the problem having a trend. So data is a general like a stationarity and ADF test. So ADF means augmented Dickey Fuller test. So the problem having a trend in your data is a general in a univariate time series modeling. The stationarity of time series means that a time series does not have, yeah, you can say a long term trend. So it is stable around the same axis. If not, you say that the time series is non-stationary. So AR model can theoretically have a trend coefficient in the model. So it since the stationarity is an important concept and the general theory of time series. It is a better to learn how to deal with it right way. A lot of model can only work on a stationary time series. So a time series that is a strongly growing or diminishing over time, it obvious to spout. But sometimes it is difficult to tell whether a time series is stationary. So this is where the augmented Dickey Fuller test comes in useful. The augmented Dickey Fuller test is a hypothesis test that allows you to test whether a time series is stationary. It is not. So try to understand. So some codes and Python code and like you can take a as it means in the earthquake data case we will see the p value that is similar to 0.05 the reference value, and this means that the series is a theoretical and stationary, so you don't have a change anything, apply the AR model. But if think about, if you are not familiar with the hypothesis testing, so you should know that the p value is conclusive value for a hypothesis test. So in the hypothesis test, if you try to prove an alternative hypothesis against a null hypothesis, so the p value indicates the probability that you would be observe the data that you had observed. If the null hypothesis were true, if this probability is low, you conclude that the null hypothesis must be wrong and therefore the alternative must be true. So the reference value of the p value is generally 0.05 but may differ for certain application. So next, try to understand differencing or time series. So even though the ADF test tells you that the data is stationary, you have seen that the autocorrelations is a positive where you expect a negative one. The hypothesis was that this could be caused by a trend. You now have two opposing indicators. One tells you that the data is stationary and other one tells you that there is a trend. To be safe, it is better to remove the trend anyway. It is better to remove the trend anyway. This can be done by differencing. So, what is the differencing? Differencing means that rather than modeling the original value of the time series, you model the difference between the each value and the next. Even though there is a trend in the actual data, so there will be probably not be a trend in the difference data. To confirm, you can do an ADF test again. So if it is still not good, you can difference the difference time series again until you observe a correct result. So similarly, just now you can see here, to see the whether this is the switch your autocorrelations and to the right directions, and you can compute the correlations coefficient as you did before. So the code for this can be seen. So you can see what this shift and difference data look like. In the correlations matrix, the correlations coefficient between the shifted, differencing the data and non-shifted differences data. So one more thing, just now you obtain the correlations coefficient of minus 0.37 as can be seen. So you have successfully removed the trend from the data. So your correlations is now the negative correlation. You expected if there is a more earthquakes one year, then you generally have fewer earthquakes the next year. Next, I try to understand lags autocorrelations. Beside the directions of the autocorrelation, the notions of lag is important. So this notation is applicable only in autocorrelation and not in regular correlations. So the number of lags of an autocorrelation means the number of steps back in time that have an impact on the present value. So in many cases, if autocorrelation is present, it is not just the previous time steps that has an impact, but it can be many time steps. So applied to the doctor's consultations durations example, we have already taken few minutes before. So you could imagine that doctor has a very long delay in one consultation, and that they need to speed up for the next 3 consultations. So this would mean that the third speedy consultations is still impacted by the delay 1. So on the lag of autocorrelation would be at least 3 steps back in time. The doctor consultations durations example is a very intuitive, as it is a very logical that a doctor has a limited amount of time. So in the example of the earthquake period, there is not such a clear logic that explain a relationship between past value and current value, and this makes it difficult to intuitively identify the number of lags that should be included. A great tool to be investigate autocorrelation on a multiple lags at the same time is US use and the auto correlation plot from the stats stats models package, and this code like a ACF is a short for auto correlation function. The auto correlations as a functions of lag. So note that the choice the 20 lags is arbitrary. 20 lags is arbitrary. So it is for plotting purpose only. 20 lag means 20 year back in time. 20 year back in time, and this should be enough to show relevant autocorrelation, but 40 or even more would be an acceptable option too. So autocorrelations of the differential data. So whenever we do the practical, so we will plot and we can see which autocorrelations are the important to a written only the y-axis, and you see the correlation coefficient between the non-lag data and lag data. So the correlation coefficient between -1 and 1. On the x-axis you see the number of lags applied in this case, and from 0 to 20. So the first correlation is 1, as this is the data with the 0 lags and original data. So 0 lags and original data. Look here. So in this, sometimes you can see the plots, means the some lags is the above the 0 and some lags is the below the 0. So if you see this type of the plot, so let's see, I am going to see here something like this type of the plot, and then we can easily understand where is the lag is going and not going. So I think I am not getting proper data. So let's see. Let's try I once more. Is it possible to can get a, because I have already done some specific research. So in this plot, no, it is not working. So don't worry, we will discuss after some time the price and something like. Otherwise you can go Kaggle websites also, Kaggle, and I can see the sum analysis because this time it is not working perfectly, so I think let's see, I try to once more just because I have done this project, so it is comfortable to understand these things. Suppose I analyze like a stock price and something, so try here. Let's see. Yes, so let's see, just I think right, that's okay. Now I am going to look like this. Yes, we can see here. So let's try here if you want to understand. So I hope, yeah, look here, this figure. So this figure has been given look like the sometime. I have taken the 50 autocorrelations ACF. So ACF has been, so need to first I am going to collect the data and from a Yahoo Finance. So I am collecting a data from Yahoo Finance. So GSPC, S&P 500 and VIX. Now the start, this data has been given, and now adjusting closing price. So the both price has been given with this date. Now I am getting the log and other value, and after that I have gotten the correlations between this S&P 500 and VIX, the negative correlations you can see here. Just I have written here correlations. So this one is the negative correlations between S&P, and after that I have plot here lag 50 I have taken, significant level is the 5% like a probability, and ACF SMT graphics dot plot ACF, and this data has been taken this time. So we can see here, so the ACF has look like this, and you can easily understand. So look here, so your ACF is the below the zero. So this plot means you should look the autocorrelations value that are the at least lesser than 0. So most of the time it goes like a minus 0.1 and something, above we can say the plus 1. So last 50 past 50 days we can see this type of the lag. So this means we can understand anything is below, we can consider the noise and use like a 20, use like a 20 or 25 as the minimum value is also possible. So there is no strict guidelines in interpreting the correlation coefficient. As in the some domains, data are noisy by nature. For example, in the some social statistics. So when working with the measurement from questionnaire studies, you will see much more noise than when working with the precise physics measurements. So something look like a blue areas in the graph allow you to detect the visuality which autocorrelations are just noise. Just noise. So if the spike goes outside of the blue areas, okay, here, 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 here. So outside goes the blue areas. So the spike goes the outside of the blue area means there is a significant autocorrelation. But if the spike stays within the blue areas, the observed autocorrelations is insignificant. Insignificant. Autocorrelation is insignificant. So you can generally expect the autocorrelations to be higher in lab that are closer to the present and diminished lower further away moments. So in this graph we observe the first like below -20 and something. So which is the very negative, so which is a not a normal. So it is the original data, so the correlations between the variable and itself is a always 1, is 100%. So the second spike is a correlations with like a nearest about a 0. So this is the autocorrelations, and you have a compute the before the using the correlations matrix. Now the correlation coefficient was like this one, a negative -0 point something, when you and you see this again in this graph. So the remaining autocorrelations are the less strong. So let's see. So only the few values look like up, otherwise it is going down. So this means the number of the earthquakes, number of the stock when prices, number of the times the stock prices, there will be the many like the last time. So we can expect the fewer, we can expect it can go down, and today is the, I think so, your market maybe can go down and it has a more possible. So ACF plot, so imagine a different means hypothetical ACF plot with the only one positive spikes at a lag 5. So let's say 1 2 3 4 5 6 7 only in the 50, but downside is look more. So this would be means that the that to understand this here the number of times your price can go down, down, down. So what happened? So you need to look to what happened the next year. So there were the many times, it may be the 2 year and 3 year. You can easily forecast on the short durations of the time. So it is possible it can go down. So I hope you can understand these things. Next, you can look here autocorrelation plot. You can see here, and another like a autocorrelations and PAC means partial autocorrelations. So PAC the partial autocorrelations plot is the another plot that you should also look at. So the difference between autocorrelations and partial autocorrelations is that a partial autocorrelations makes sure that any correlations is not counted multiple times for multiple lags. So therefore the partial autocorrelations for the each lags is additional autocorrelations for to each inferior lag. More mathematically you can correct, you can say the partial autocorrelations, autocorrelations conditions on earlier lags. So look like a covariance of yi minus k and k here, and similarly the divided by the square root of the variance yi by yi minus 1, and similarly we can go the y something and will multiply the variance of the y minus k and something. So this has been added a value like the correlations in the autocorrelations plot may be redundant between the one another. So the idea is easier to understand on the hypothetical example. Imagine the hypothetical case in which the value for the present lag 1 and lag 5 so are exactly the same. So the autocorrelations would tell you that there is a perfect autocorrelations with the both lag 1 and 5. Partial autocorrelations would tell you that there is a perfect autocorrelations with the lag 1, but it would not show the autocorrelations for lag 5, as you should always try to make a models with a lower numbers of variables necessary. It would be the better to include the only lag 1 and not lag 5 in this case. So you can compute the partial autocorrelations plot using a stats model as shown in PACF is a short for a partial autocorrelation functions. So look here, just you can see here there are two autocorrelations, and both the data look like that, but I try to look here, it has been seen look like this, and another it has been shown like this. So some Python code can describe here. So you are going to get here the autocorrelations, and we need to create another code. We can easily get a partial autocorrelations. One question has been always added: how many lags to include? So now the big questions in the time series analysis is always how many lags to include. This is called the order of the time series. The notations of the AR1 for the order 1, ARP of order P. So the order is up to you to decide. Theoretically speaking, you can base your order on the PACF graph. So the theory tells you to take the number of the lags before obtaining an autocorrelation of 0. All the other lags should be 0. So in the theory you see great graph where the first spike is the very high and the rest is equal to 0. So in those cases the choice is easy. You are working with a very pure example like AR1. So another common case is when your autocorrelation starts high and slowly diminishing to 0. So in this case you should use all the lags work. The PACF is not at 0. Like this. Okay. So in the theory you often see the grid graph and where the first spike is the very high and the rest are the equal to 0, and those cases the choices is easy. You are working with a very pure example AR1. And another common case is when you autocorrelation start high and slowly diminish to 0. So you should use all the lags of the lags where the PACF is not at 0. As in a practice, it is not always the simple. Remember the famous saying, all models are wrong, but the some are useful. It is a very rare to find a case that perfectly fit an AR model. In a general, the auto regression process can help to explain the part of the variations in a variable, but not all of it. So in the earthquake example, there is still a bit of the partial autocorrelation further the lags, and it goes on until a very far lags. So there is even the spike the PACF of lag like a 10 and 11. So this could be a mean the many things, and maybe there really is the autocorrelations with the lags far away. So or maybe a hidden process is underlying, that is the AR model is not capturing them. So in a practice you will try to select the number of the lags that gives your model the best predictive performance. Best predictive performance is often not defined by looking and autocorrelation graph. Those graphs give you a theoretical estimates, but the predictive performance is best defined by doing a model evaluation and benchmarking using the techniques that you have seen. Now AR model like a XI, XT, you can write here the summations of the I will start from the 1 until P, and gamma you can say the sigma xt minus I plus error term I. So this formula xt, it is the current value, xt as a current value, and it is the computed as the sum of the each lag xt minus I to multiply the coefficient of phi I for the specific lag, the error et at the end of the random noise and cannot be predicted but you can estimate. So after some time we can see also how to do this process, so and then how to apply here model. Thank you for today.